All right, so first of all, let me thank the team, because part of the slides, all the activities are done by these guys. I'm just, ask, please do this, and they are very good on doing that. And also let me thank the funding agencies, because actually in the last years, we were very lucky to get a lot of funding, especially from company. I wanted to thank this robotic company and these companies which are basically on security, which they are sponsoring a lot to this IC machine work. Also, I wish to highlight that I'm currently peer editor of peer physical review applied. So, and this topic fit very well in this journal. So if you have paper, please submit, and I will deal with that. I will be very kind, this community. All right, so let me start with the outline of the talk. So I basically discuss about two things, which I think are going to be very impacting the next year. One is, let me see, okay, now is neuromorphic computing, and the other one is actually IC machine, which can be implemented in two different ways, using p-bits or using dynamical systems. So let me start with a motivation about this. Why we want to do that? We want to develop technology on these two directions. So recently, we wrote a paper where we highlight that one of the main challenges and the main opportunity for spintronics is the development of memories. You already have in your phone, Samsung phone, STM-RAM memories. You can find in Huawei, and a lot of companies already use this. And then people are start to explore applications which can be a generalization of memories, in particular for logic. In order to do effective on this type of design, you need to have a co-design approach. So basically, the old approach is that you design elements in terms of memory, device, algorithm, all separately. But now the key winning point of this approach is that you do a co-design of all these layers together. And doing that, you can also attack applications which are not anymore conventional. For example, you can work with unconventional computing. And I think this is a very good opportunity for 3D magnetism. In particular, if you go here, so here you see you can have something which can be memory or can do nonlinear operation, which can be either integrated and also can be very fast. Because ferromagnets and antiferromagnets have an intrinsic resonance which go from gigahertz to terahertz, so they can really work at this frequency by design. And the main point here is that you can develop all these non-conventional applications if you start considering how to do integration among different technologies, right? For example, you can do heterogeneous integration. So basically, where you combine CMOS plus, X, let's say it can be optics, something from optics, spintronics, and anything. This is actually something which is before the monolithic integration, where you have everything on the same chip. And we have an European project where we are trying to do this with spintronic and CMOS. But also, right now, all these companies are developing something which is in the middle, so which is basically chiplet approach. So here you have different nodes of CMOS, and then you can have each of these chiplets can be, let's say, only from photonic technology or optoelectronics or spintronics. And then the challenges here are basically all these communication, the protocols for doing, for exchanging information about this. So let's consider you can develop a chiplet which is based on 3D magnetism. So which right now is going to be absolutely independent on the rest of the technologies. But just considering this type of approach. All right, so after this brief introduction, let me go too much into the details and give you some ideas. In particular, I'll be very basic, so please forgive me if you know already everything. So I'll try to be, very, very starting from scratch. And of course, you know that the starting point is this equation, which is the idea of perceptron, or the idea of a neuron. And this neuron, of course, can be coupled together, and then you can have a complex network. But basically, what this neuron does is you have different inputs. Then you weight this input for this weight you have basically as W1 and so on. Then you adapt all of this. Each neuron has a local bias, which can be seen like a battery. Then you apply this local bias, and then at the end, the neuron do a nonlinear operation, which convert basically this MAC operation in something which is mapped in a nonlinear space. And thanks to this nonlinearity, which is the key element here, you can model almost everything. So you can use this neuron as a building block of very complex network, and then you can build everything. In order to build this, actually you need to adapt these parameters to the data which describe the model you want to model. And there are a lot of different nonlinearities, for example, sigmoidal ReLU. And the good thing is that this nonlinearity can be implemented easily in spintronics or using magnetic materials. And the key challenge here is to find out an algorithm which uses the gradient descent, which can be applied directly on chip. So if you do this in software, it's very, you can program very easily. But then when you try to reduce the energy and then you map all this structure in the hardware, of course you need to find some way to up this gradient descent on chip. And we know already, we have already some results, that you can do this with magnetic tunnel junction. And of course, I think you can do also with much more complex structures. All right, so this is the starting point. But in order, this was like 50 in the 50. So, but now, now why we are in this age? In my opinion, we are in this age of AI because there is another neuron which is very important, which is the convolutional neuron, which gives really a push of this technology. And the starting paper is this one. So in this paper, people put electrode directly in the head of a cat to see how the virtual cortex works. And this was inspiration for conventional convolutional neural networks. So basically now, the MAC operation is done among the input, which can be an image, for example, and filters. And you do this operation, as you can see here, and then you create the so-called activation map. And then this activation map actually can can extract information from this image in a proper way. And then to each of these elements, you apply still a nonlinearity. These are an image which I took from basically from internet. And if you compare this image with the one of this paper, actually you see a similar thing. So you have different layers. So the first layer of your cortex, visual cortex works like this, extract simple details, and then those details are added up while you move toward the brain. So the convolutional neural networks works like for this reason. Then you have a lot of way to improve, to create a lot of details here, the way you calculate the convolution, the losses, a lot of application. You have a lot of possible direction here. So the one I want to share to you, with you today, is the batch normalization. So if you look to the state of the art of neural networks, actually this block is almost in all of them. And I think that I will show you how it works. You can implement this block directly with a 3D magnet. So let me start with the basic of batch normalization. So before your standard neuron, you have another neuron which collects all the inputs. So basically now you have somehow a neuron with memory. And while doing that, once you collect all the information, basically you calculate the average, all of this information, and the variance. And then at the output of this neuron, you have basically a quasi-normalization procedure. So basically you remove the average, and you convert this distribution of data to have unit variance. And in this batch normalization neuron, you have two parameters which has to be trained. One is a scaling parameter here, and one is a shifting parameter. So still, you do this operation, then you have additional 2 parameters for training. Of course, you do this for a layer of neurons, and if the data are a lot, you can basically organize the data in a batch, and then you can do basically, for each batch, you can calculate the average and the variance, and then you can basically create the so-called moving average and moving variance, which can be used for your network. So you see here, actually, you have a lot of data. So you can actually, if you are able to do this in 3 dimensions, you can do actually the calculation by using this type of scheme. So we have some ideas, so probably if someone is interested, we can talk about this after. And I can tell you that to do this in hardware is very complicated. So you can know, with the current technology, always all the people use CMOS. So there is not a very efficient way to do that. So now let's come back to the neural networks. And we have, as you can see here, so we have convolutional layers, fully connected layers which are based on standard neurons. And then we have, at the end of the network, typically the network which do classification, a softmax layer. This softmax layer is basically given by this activation function. So you have T, which is the temperature you see, somehow is called a Boltzmann distribution. And when the temperature is very low, so you have somehow hard targets. So basically, they convert the inputs of the last layer to a specific decision. In this case, we have this image which gives a dog. Now, if you change the temperature, for example, you go a larger value of T, let's say 10, these hard targets are converted to a soft targets. So even with the same inputs, at the end you have something which gives you the probability. So for example, we have 90% probability that this is a dog, but you have also finite probability, small but still finite, that this can be also not a dog. So I like a lot this because we can do a very nice operation. I will tell you in a while. All right, so now we have all the three main ingredients of neural networks, and there is a lot of effort doing especially by Julie Grolier group and Vincent Cross, where basically they create this neural net, this spintronic-based neuromorphic computing, and we also take inspiration from them and also develop in our team some of this. And in particular, we focused on the following. So we know that we have software implementation, and then we know the weights of the network, and we want to transfer this weight in hardware. So when you do that, of course, and you do this transfer, what you get in hardware is not always exactly the same of what we have in software. In particular, for example, we did several trials. I will share with you the one about the radio activation function we implemented recently. So we had basically a standard neural network. We trained this network with MNIST database, very simple database. And then when we emulate the transfer learning from software to hardware, so what we did is we changed all these neurons here from ideal to non-ideal, and the activation function is sampled by what we found out experimentally. So basically, experimentally, we take this data from different devices, and we've identified the range of variation of those, and then we have sampled all this layer with different activation function from this. And then, without an additional training, we evaluated which is the accuracy variation with respect to the ideal case. This is the distribution. We did like 1,000 trials with different networks, and we saw the distribution is close to the ideal value. So basically, the conclusion is that if you do transfer learning, at least for this simple network, from ideal software to hardware, and use a device which have this spread here, we still, without additional training, we still can use this network for edge devices and so on. So you don't need to do additional training. This is a key point to save the cost of deployment at the edge. All right, so this is a very simple way to do transfer learning. So you have the same structure of the network, and then you map the same structure of the network in hardware. But of course, this is not always possible when you work at the edge, because the model that people are now developing are very, very complex. So you have a billion of parameters. So an effective way to do transfer learning now, it's basically using a different concept, which is called knowledge distillation. So here you have basically a big network here, which we call teacher model. And we want to transfer to a smaller one, basically using some techniques, all the know-how that you have here. So basically, we want to teach someone which is smaller, almost the same thing. And you can do this, I mean, this is open research topic now. And you can do this in different ways. For example, you can do using offline distillation, which means the teacher is fixed, and then you just change the weights of basically the student. Also, you can do like a mix, so you can have feedback. So this is a very hot topic now. So you really, if you're interested, you can give a look. And one way to transfer this knowledge is basically based on the use of response-based knowledge. So basically, this is the information we have at the last layer before to apply the softmax. And what we did is we tried to extract from this last layer something which is called dark knowledge. to be honest, I'm in love with this concept because I think it's really, really useful. And at the end, we are able to deploy very small model in the phone, which works exactly very close to the big model we have trained with billion of parameters. So it's really, I think this is a direction which is going to be, we will listen a lot in the next year. All right, so let me tell you more about this dark knowledge. So if we come back to the softmax, you remember, by changing the temperature of the activation function at the end, we can have different hard and soft targets, right? So we can have somehow extract information from there. All right, and so if we do that, we can create a scheme for a neural network, which is composed by 3 elements. So it's the teacher model without the softmax. So we extract here somehow some information which is at temperature different than 1. So we have somehow dark knowledge. This can be dynamical too also. Then we create, we have this student model, and from this one we extract same dark knowledge and also the hard knowledge, which basically are targets. And then we have a combination of loss which come from this and the distillation loss. So basically we can weight this also dynamically. And while doing that, so actually we will have basically, we transfer the information from the teacher model to the student model using not only the data, which are already available, but also some dark knowledge, which is in the trained model, that you cannot see if you use softmax equal to 1. And these are some calculations, for example, that we did, you see? And actually, you see that if you increase the temperature, you can find that the value of the probability goes from 1 to 30%, in this case for this 9, for 1 goes to 25%. You see, and all of the information which is inside the model actually emerge, because you have some probability to have different layers. Yeah. And this is actually some ideal calculation here by using softmax. Of course, you can use this in very complex system, and what we find out is that there are different ways to extract dark knowledge, and I'm not going too much into the details here because we are patenting that. But basically, we can use a different nonlinearity, which goes beyond the softmax, to extract a better dark knowledge. And we understood that, we call it here door, but we understood that we can basically extract this dark knowledge by using the nonlinearity of magnetic tunnel junction, or magnetism in general. So actually, this is very effective because using the same device, by just tuning some current or voltage, you can extract a lot of different layers of this dark knowledge dynamically. So it's really somehow tunable extractor that you can do in spintronics. All right, so when you then look at the books to try to understand better, so you go to the very basic neuroscience book, and then you try to understand how you can combine these multiply, accumulate blocks, convolutional blocks. Then you figure out that all the neurons work totally in different way. So they use somehow the so-called the concept of spiking. Here is actually a summary I took from this book. So the neurons are typically a resting potential. Then you reduce this potential, they do nothing. But if you increase the potential, exists a threshold above which you see some variation, strong variation of the voltage across the neurons. And then according to the amplitude of this pulse, you can get 2 or 3 different spikes. But still, after each spike, the neuron comes back to the resting potential. And then is ready to start again. And this actually currently what is implemented in a lot of chips. And this is the way to go for saving a lot of energy. People call this third age of neural network. And the key trick here that the neuron uses is to combine two physics. Actually, one which comes from electrical signal and one which comes from chemistry. And then we try to understand, because, and what we understood is that actually you have at the resting potential, you have, this is a very simplified model of the neuron. You have a membrane which separate in one side the majority of potassium ions. In the other side, the majority of sodium ions. And then you have this negative voltage. So as the voltage increases from external source, what's happening is that the permeability of this membrane change. And then you have that the potassium atoms, ions, move to the side of the the sodium ions move to the side of the potassium ions. Then you change the voltage across the barrier. And then what's happening is that above as the voltage increases, what's happening is that the permeability of the membrane change again, and then the potassium are moved to the other side in order to put down again the voltage. So as you can see here, after the spike, so basically the ions of potassium and sodium are switched. So actually the neuron cannot spike anymore. And then at this point, the sodium-potassium pump start playing a role because it switch back slowly all of these neurons, all these ions, and then after this process is finished, you are ready again to basically to spike. So this is actually something which combine, two physics, right? So when you try to develop a model to design all of this stuff, neural network using a simplified model, you are lost in a zoo. There are a lot really of models, from Lie integrated fire, H model. The HH model is the closest to the real spiking behavior of the neuron. And then you have the model. In simulation works very well. And then you try to do this in hardware. So this is very complex CMOS implementation of this. And then you can do in spintronics. There are a lot of different solutions. And we proposed recently a solution which uses MTJ, where you combine the spin torque together with thermal effect. And we found out that using a spin torque oscillator here, so basically you can tune the frequency of the oscillation in this way, combined with the idea from this paper where we have basically temperature effect because you have two MGO layers. So actually you really control here the spike, but here you need a reset. So combining these two, we come out with a device which actually gives us a spike behavior which is compatible with HH model. See here, for example, some calculations. This paper has been published. And we were able to map almost one-to-one, the HH model with macrospin approximation del LG. So you can say that to me that this is just theory, but of course we already have this. We find out this also experimentally, and we are writing now the paper where we combine this MTJ already in real, so in hardware. And these are for neurons, but of course this idea of spiking is not only applicable to neurons. And I think that one of the very promising direction of this is the use of this technology for IoT, and in particular in this paper which come out last month, there is a way to synchronize data from a network of sensors using these spiking models. And yeah, if you're interested, we can also talk about how to use 3D magnetism to develop sensors and spikes. So basically, you can have different layers. Each of these make different operations instead to be, only one. But anyway, if you are interested, we can discuss about this. All right. So let me talk quickly about the few more things about neuromorphic computing. One is, every one of you knows already reservoir computing because I think most of the community is working on this. And also we are working with Dennis to implement some reservoir computing stuff. And what I can tell is that in order to be aware if your approach is good or not, we found out this paper published by the group of Thomas Mikolov, which basically is the founder of the protocols to map for ChatGPT. So actually, he was really leader in developing this protocol, this transformer stuff. And the main results of this paper is this one. So reservoir computing learn faster and have comparable accuracy, right? So at the end, this means that if you try to compare just the accuracy, you don't get any real information because the accuracy is the same. So you should find a matrix which at least is used to compare the basically the velocity to the accuracy. And of course, you should do this not in simple problems, but in problems which clearly have different graph. And in this paper, there are some examples, at least 10. So now you have the problems. You know where the reservoir computing is better. And in order to evaluate the performance, you can use the metric which is called the weight. So basically, you select different points in the training step, basically different number of iterations. And for each iteration, you calculate the accuracy, and then you basically weight this accuracy using this sum. This is good because after like 10, 12 numbers, this value saturate. So you can really find out these very good metrics. And then when you try to compare, to use these metrics with different problems, using different approaches, comparing with transformer and other technology, actually you see that these are reservoir computing based approaches. They go very fast to high accuracy. Here, of course, they go fast at some point, but the transformer at some point improve much better. So it's really still open point where to go. However, if you think you have very good reservoir computing, please benchmark on this problem if you want to be effective. So finally, there is something which goes beyond reservoir computing, which we call dynamical neuron. So now you have strong nonlinear system, but in addition to that, you have a parameter which can be trained, which is actually, let's say, a control parameter. For example, for magnetism, it can be VCMA, it can be field, right? So we don't use this, but I think because this is much better than reservoir computing, so I think we should try to go in this direction. We did some trial with spin torque oscillator, right? And we have very simple tasks. And actually, we were able to separate, you see here, also different class in this phase space. And very high accuracy. And yeah, so this is still open direction. So of course here, because you're minimizing this function, you cannot use the gradient descent. You need to use optimal control T, which is a bit different, a bit more complicated. But I think they deserve to be investigated. All right. So let me move now to the last part of the talk, which is more on Ising machine. And let me start from the beginning. So actually, the Ising model. So here you have an Hamiltonian, which is defined by two parameters, which is J and H. So basically, this is an energy. And this M is a vector of binary variables, which define this discrete energy landscape. And typically, the problem of Ising model is to find out the vector M, which give you the minimum of this energy. So this is a discrete problem. So basically, you cannot apply gradient descent. So you cannot apply standard techniques. And this is why it's very complex, because ideally, you should make a combinatorial process to find out the minimum. But practically, there are some update schemes, including probabilistic computing, which have update equations, which are ready, basically somehow reduce the search in the phase space. So the search is focused in a smaller subspace. And of course, you can do this in different ways, and this is how we do with probabilistic computing. So we have the updated equation of the state, which depends from a random number and some nonlinearity, which is basically given by a Mach operation. So basically, you have all the neurons, all the spins, which are weighted somehow. Then a nonlinearity is applied. You apply also some randomicity, and then you binarize using this sign function. So this is very hardware-friendly approach. So because you have binary variables, Mach operations, which actually are very, very hardware-friendly. And recently we wrote a review with Kerem and Shunsuge, where basically we describe the stack of this probabilistic computing approach, so which are the main problems. and which can be the type of implementation. And of course, you can do this in CMOS, full digital, or you can do, somehow you can wish to do this in basically using spintronic technology. Or of course, you can do like using heterogeneous scheme. So at the end, we can think that this can be a block of a chiplet architecture, right? Which can be like a coprocessor of your CMOS hardware. All right, so now we have the model, right? So how we minimize this energy, how we find out this vector? The key answer is using annealing schemes. All of you are aware about this annealing scheme because you can apply materials. So actually you can improve the performance of devices, but you can do also this at software level. And for example, very standard approach using classical thermal annealing. So you have your system, your temperature that is a lot, is very big, and then you slowly reduce the temperature on time, and then at some point, you get stuck in a local minimum or in the best minimum, right? So you run your algorithm, and the way you control this temperature in probabilistic computing is by changing this I0 as a function of temperature. These are some examples for spin glasses. You see, you start from very complex pattern, then as the temperature reduces, you see you move towards something which it's more realistic configuration of domains. But this is very simple, right? So much more complex approaches are basically the parallel tempering. Here we take inspiration from the parallel simulated tempering, which has been developed by the group of Parisi. And now basically each replica works at fixed temperature. So, and then you have a gradient of temperature among the replicas, you see here. And in addition, so each of the replica evolve independently. But then you integrate this with some operators, which can exchange information. So at the end, what's happening is that if you find a better state at high temperature, somehow you do some diversification, you transfer this information to the lower temperature replica. Of course, this is a very simplified version, but you can really do this. And one of the operators you can use in parallel tempering, which I like a lot, is the simulated quantum annealing. So now you add somehow an exchange, a sort of exchange interaction among closed replica. And this emulates more or less what's happening in the real quantum annealers. So actually you have this interaction among all the states. And this interaction transfer field is called also increase as a function of time with a proper function. And then at some point, because of the exchange, which is positive, all of the replica collapse to the same state or to cluster of states. And then you can identify which is the best state. And this is very promising, actually. It's really, really impressive. Just to let you know the difference between standard annealing and simulated quantum annealing is that if you look here, each replica in the simulated quantum annealing, in the classical annealing, actually run independently. So you can run like 1,000 of times using different seed, of course. But then in the quantum annealer, or simulated quantum annealing, actually you have this exchange interaction which increase. And if you think about this in terms of 3D magnetism, right? So you know there is this RKKY which can be controlled by voltage. Somehow you can apply voltage, put this RKKY at 0, and then you can actually increase or decrease the voltage in order to somehow to couple all the layers. And yeah, this can be something that can be done in hardware directly, hopefully. All right, so now we have almost everything. So the model is set. We have the equation, we have the energy, we have the way to minimize the energy. And now the key point here is that we want to sample the Boltzmann distribution here. So we cannot do parallel strange thing. So we need to follow a rule. And this rule is set by the update scheme. So typically, in order to sample the Boltzmann distribution, you need to update each spin one by one and then calculate everything. And this is typically what the nature of materials is doing. So they do you have a network of interacting elements. Sometimes one of these change, and this change actually is transferred to almost all the others. This is somehow called the asynchronous update, right? This is actually the key point. This is why it's very hard to do this in GPU or high parallelized soft hardware. because you need this type of scheme. So at the end, you don't get too much advantage. And and this is something that you can understand is basically called also Gibbs sampling, and this is what's happening in real systems. All right, so when we try to do this update, for example, and we have a fully connected graph, so what you do, you need to do this sequentially. So fully connection, one by one. You cannot escape. So there's no way to parallelize anything. So it's very, you need a lot of time for that. And this is actually called synchronous Gibbs sampling because we use a clock. So this sequential update is basically synchronized to a clock, so it's not totally asynchronous. Then, of course, not all the problems are fully connected. So you have some problems which are actually sparse. And then when you have a sparse graph, you can apply standard graph coloring. So you create colors in this graph. For example, as you see below here. So you apply this graph coloring algorithm. You have the colors here. And then, because they don't interact, here you can update all the cluster at the same time. So this is the first way you can parallelize anything. For example, here you have first red, blue, and green. So you see, you move from 9 sequential operations to just 3. And you can do this, for example, using directly hardware like some asynchronous clock, which can be implemented, for example, using a well-precise phase shift. It's very complex to do. Or you can use, for example, connection of finite number of ring oscillators. Of course, here, because they are finite, you have some conflict. Still, even if you have conflict, actually, when we benchmark a very complex problem, we find out that still the performance are comparable with the synchronous Gibbs sampling. Still not so good, but at least comparable. So we can have, let's say, a starting point where we can apply then the full synchronous update. This was very boring because I explained the algorithm, so all the challenge, but I think there is a lot of stuff. Now let me tell you why we want to do this, actually. We are really focusing on IC machine, why people are giving us money. So the main reason is that there are applications in different fields, but the most promising, the most economically impacting is the combinatorial optimization world. So basically, why is so impacting? So if you just look to any problem of companies, so for example, any company has some logistic problem. They use some software to solve it. You have job scheduling, airline routes, and because all the resources you have are finite, so you have 3 van, 4 camion, 1 car, 10 billion, so all the resources are finite. All the problems you have to solve are combinatorial problems. And there is a lot of algorithmic stuff which tell you that these are very complex to solve. If you're interested, we can discuss after. But the economy is very important. So if you find for a company a better solution, you save not only money, but also you reduce your carbon footprint. So this is why it's very interesting. And of course, this is the process to do that, and there is a lot of competition. So if you want to go in this business, you have to compete with a lot of companies. So let me show you a very simple process for doing that. So you have, let's say, backsat problem is very useful for benchmarking your IC machine. So we know how to map this problem is the icing model. You see here the icing elements. And then we run our algorithm, very simple one for this case. And we find out the optimal solution, because for this problem is known, in 600,000 iterations. And if we consider we have 100 variables, the combination of this problem are 2 at 100. So it's way larger than that. And of course, here you use parallel tempering. You see from the colors, we have 4 replicas, but there's a lot of work trying to find out the optimal number of replica, the optimal temperature. And we were also able to solve problems which are more complex, like weighted maxat. We also solved the maxcat problem. And so we can also we can tell you that this is really very general. So if you are able to have very good IC machine, you can map almost all the combinatorial optimization problems. Still, everything here is in software, GPU, but the main direction we have is to try to find out a spintronic solution. And we are inspired by this nanosecond random number generator. In particular, we took the data from IBM, we create a model, and we, in software, emulate this IC machine, which use the parameters for emulating this magnetic tunnel junction. So if you look at the problem we solved, actually we were able to convert the solution in less than 60 nanoseconds. So as I always say, so if we are wrong here by 3 orders of magnitude, so because of course it's software, right? So it's like 50 microseconds. At the end, if you do this in FPGA, you need 50 milliseconds. So still you are 3 orders of magnitude faster. So the potential is really, really there. And we have a lot of collaboration. I know people are really working on doing this, either in Fugami and Karen, and Yansu Yang. And we are also working with Yansu on scaling this to kilo qubits. All right, so let me show you the last slide about this topic and quickly move to the next one. So actually, we basically are able to solve combinatorial problems different ways. We are able to map this actually in FPGA. We did this with Karen. And these are actually the results we got at the state-of-the-art machine. So we are able to go to the 95% solution better than the best max-sat solver. But still, we are working on this to face the 100% solution. We are still very far away from the best. So it's between 95 and 100% something happened. And we try to understand what's happening. And probably one of the key reasons can be a weak random number generator that we have in FPGA. And to overcome this, actually, we had a collaboration with Pedram, I'm here in Northwestern, where we use VCMA to generate this random number. And then we change the CMOS implementation based on this LTSR to something which use VCMA random numbers. And what we found out is that we can use somehow a dynamical way to the accuracy, so we can increase the accuracy real time. And then at some point, we are able to converge, to the minimum, probably, to the solution, in the solution very quickly. Of course, you can compare all of these statistics and so on, and we did this with Eleonora, and we are submitting a paper about this, where we show a full comparison, all of the linear scheme and the performance of this. All right, so I have like 2 minutes and 20 seconds. So I will give you a different overview. So right now we are using probabilistic bit. These are discrete, basically. So you sample at some point, you have the digital stuff. But you can do IC machine with time domain, with dynamical systems. And there are a lot of solutions here, in particular one which use chaos. So this is why I encourage vortex people which work on vortex oscillator to look at this type of machine. And also one is based on spin-torque oscillators, which actually looks like something which is close to what we do in spintronics, right? So actually you have the same equation, but now the dynamical update equation is the same model, is different. So you have an injection, a spin-torque oscillator. And if you do the injection locking at the same frequency, you have only one phase of difference. But if you do this parametric locking, you have a degeneracy in the locking state. So you can have 2 states. And this is 50% probability. So you can have one or the other, no problem. And then actually here you can see that this can be used to create a binary variable for the oscillators. Right, so the 2 phases give you the information. And then you can couple this oscillator together and in order to have network oscillators. So of course what we did is we tried to explore this performance in software. And then we implemented the so-called Kuramoto model, which can be used also for vortex-based spin-torque oscillators, or the Slavin model, which can be used for uniform spin-torque oscillators. And these are actually the results we published in the last paper. So you see performance getting similar. So even if you have coupling between power and phase in spin-torque oscillator, you still can get performance which are comparable with the Kuramoto approaches. And then we compare this. Of course, we cannot scale too much in software sliding model because we need double, 2 times the memory with respect to Kuramoto. But performance are pretty much the same. And we also compare with the state-of-the-art solver for MaxCut, which is the Gemma's Williamson algorithm, which assures you to have 0.87% of the solution. And actually, we scale much better. In particular, here we got like 20 million nodes, which is currently the state-of-the-art of nodes for this type of machine. And you can do this in different ways, using different technologies, 3-terminal, 2-terminal device. Then you can compare this with probabilistic computing, so you can create collective Ising machine. And if you look to the time scale of the solution, so actually you work, you approach solution nanosecond scale, right? So it's really, in particular, the dynamical system can go much faster because they are linked with the intrinsic oscillation of the spin of the oscillator. So this is actually the last slide of my tutorial. Let me show you that we organize a conference on Ising machine. Next year will be in the US, Chicago. And also I encourage you, if you are interested, to participate to the school we organized this year in Messina in December. And let me thank Giovanni, because very important for us. Thank you.